Hello, everyone. Welcome to this ACUR ANU student presentation session. We acknowledge and celebrate the first Australians on whose traditional lands we meet and pay our respects to elders past and present. My name is Sneha and I'll be chairing today's session. I'd like to tell you that we have 3 student presenters today, Ziqi, Fletcher, and Tiarne. I would also like to welcome the judges, Tui and Anne, who are here with us today. And with this, let's start our student presentations. Our first presenter will be Fletcher. You're ready to go, Fletcher.
All right, thank you. So we'll get this chemistry macro and micro session underway by starting at the very, very micro scale. In 2016, the Nobel Prize in Chemistry was awarded for the design and synthesis of molecular machines. So when we talk about machines, we might think of something like a car and its engine, which takes one form of energy, so the chemical potential energy in its petrol, in the fuel, and converts it into another form of useful energy, like moving the wheels around to move the car forwards. Now, molecular machines are things that do this kind of energy transformation, but at the molecular scale. So half of the Nobel Prize was awarded to Feringa for the design and the synthesis, so actually making this kind of fan-like molecule that you can see in the little video on the slide. And so this, the top part of the molecule moves around and around in one direction, just like perhaps the axle or the wheels might on a car. Now, the other half of the Nobel Prize was awarded to Sauvage, and his work primarily focused on these molecules called catenanes. And the simplest form of a catenane is a 2-catenane, which consists of 2 interlocking rings. So this smaller blue minor ring is threaded onto the big green ring, and it can move around it, either left or right. And if we can get this minor ring to move in one direction, say we get it to rotate clockwise, then you can see how a catenane might behave, again, like an axle or like a wheel on a car. And so even though Sauvage was awarded the Nobel Prize for his work on these kinds of molecules and coming up with the idea that something like a catenane might behave like a machine, him and no one else since has actually been able to make one. To make a catenane where the minor ring moves repeatedly in one direction. So the motivation for my research was to try and define conditions that can get this minor ring to move in one direction. And so I approached this project from a computational standpoint. So I wasn't in the lab, I didn't play with any chemicals, but I worked with my supervisor to try and come up with a really simple physics-based simulation that first tried to capture the motion of a catenane, so tried to simulate this minor ring moving around the major ring, and then secondly tried to get this minor ring to move in one net direction. And then thirdly, if we were able to achieve that, then to try and improve the unidirectionality or make it spin faster. So firstly, I said that a machine takes one form of energy and turns it into another. And so our sort of primary energy source in this case is some random vibrations of water molecules. So these red and white blobs you can see on the screen are water molecules. And like all molecules that are above absolute zero, they vibrate randomly. And so a water molecule might happen to vibrate and collide with the minor ring and cause it to move. The problem with random vibrations are just that they're random. And so it's equally likely that another water molecule might come along and knock the minor ring in the other direction. And so if we set up a simplistic simulation that represents the water molecules and how often they collide with our minor ring and how strong those collisions are, and we let it run for a period of time, and we take a photo of where the minor ring is at the end of the simulation, it forms this kind of normal distribution where more often than not, the minor ring ends up exactly where it started, at 0. So it gets knocked to the left as many times as it gets knocked to the right. And so if we just have this molecule in a beaker and we think of it like our car, our wheels are turning forwards as many times as they're turning backwards. And that's not a very useful machine. But what to this level it proves is that I've managed to make a simulation that replicates the kind of behavior that we're expecting. So a couple of weeks into my research project, we'd achieved step one, and now we had the slightly more difficult challenge of trying to get this minor ring to move in one direction. And for that, we turned to the literature. And so there are a number of people that after the Nobel Prize, all of a sudden got very interested in this field. And they kind of went for the cutting edge of computational chemistry to try and solve this problem, where you represent every single water molecule and you track how it moves and interacts with every other water molecule. And it's very, very computationally expensive to do this kind of experiment. Now, in my undergraduate research project, I didn't have access to supercomputer time, so we weren't able to take this level of approach. But what we were able to learn from these attempts, which again, notably, were not able to actually produce a catenane that behaved like a machine, was that you need some sort of secondary force. There needs to be something else acting on the minor ring to get it to move in one net direction, because if just left to the random collisions with the water, it goes nowhere. And so the simplest way to introduce a secondary force is to attach blocking groups to the major ring. And so these kind of behave how you might expect from the name. If you're the minor ring and you start to move towards or approach these blocking groups, then you get forced backwards. You don't like to share the same space. They're really big and bulky, and it's uncomfortable to be near them. So if these blocking groups are really, really strong, and our minor ring is the little blue ball, as soon as you start to approach one of these blocking groups, then you get forced back to where you started. You don't have to wait for a water molecule to come and knock you back in that direction randomly. You automatically feel this force. And so if we again look at our histogram of the final positions when these blocking groups are really big and strong and powerful, then the minor ring always ends up where it started, because as soon as it moves off its starting position, it gets knocked back to where it came from. If, however, you make these blocking groups smaller and you kind of reduce the force that they exert, then sometimes the random collisions with the water molecules are strong enough to get you to move around to the other side of the ring. The problem with this case, however, is that our blocking groups are symmetric. So there's as much resistance to moving left as there is to moving right. And if you run your simulation, again, our car is moving forwards as often as it's moving backwards. And that's not a very effective machine. And it's not unidirectional motion. So to try and get this motion to be directed, then we can play with this secondary force. We can change the chemistry of our blocking groups. And the simplest way to do that is to make them asymmetric. And after fiddling around, we found that the best way to get this minor ring to move in one direction is to produce a sort of potential landscape that looks like this. So if you get bumped by a water molecule and move to the left, it's like climbing up a gradual slope. It's reasonably easy to climb your way up a gentle incline. But if you get bumped to the right, where the blocking group's a bit bulkier and bigger, it's like trying to climb up a cliff face, and it's very, very difficult to do. So if we run our simulation and we have a look at how many times our minor ring is able to climb up the gradual slope compared to how many times it can climb up the cliff face, then we see that we start to get, in 2% of cases, it able to get over the gentle slope, and only 1.3% of cases to overcome the cliff. And so we're starting to see some directed motion. We're starting to see the minor ring move anti-clockwise more often than it's moving clockwise. And we were able to achieve a net rotation by introducing this asymmetric secondary force. So this is unidirectional motion of a catenane, and we've, even just through a couple of simple steps, been able to define a chemical system that should be able to operate like a machine. But we achieve this with enough time to try and improve it. And so the the optimum mechanism for improving this unidirectionality is to blink these blocking groups on and off. So if you imagine, again, when they're really strong and they're connected to the ring, you're stuck where you are. But if we react these blocking groups off the ring, then suddenly you're free to diffuse. And sometimes you might end up on the other side of this big cliff, such that when it gets reattached, you slide down the slope into the next kind of low potential area, the next comfortable area. And that is seen as a net transport. You're starting to revolve around the major ring. And so you can vary the time that these blocking groups are on the ring and off the ring. And you end up with a rotation that's over 100 times faster than when these blocking groups were always attached to the ring. So out of my research, I was able to develop a working simulation of a catenane and then find that an asymmetric secondary force can get it to move in one direction, and that by blinking it on and off, we can make this in unidirectional motion faster. So we came up with a simulation, and that can start to feed into experiment to hopefully actually be able to produce and make a 2-catenane that exhibits this kind of machine-like behavior.
Awesome. Great presentation, Fletcher. Thank you for that. So now let's open for Q&A. Judges, do you have any questions? Also, the audience, if you have any questions, you can please add it in, you can put it up in the chat or in the Q&A. Or you could even raise your hand and we could unmute you. Yep, judges, please go ahead.
Very interesting and excellent use of graphics, Fletcher. I just wondered whether you could finish up the presentation by, you spelt out to us what the next steps are procedurally in terms of undertaking some experimental work to move this out of a computer and into the lab. What happens when we get it out of the lab and into the real world?
So there is a lot of scope in this field, and the kind of general consensus is that potentially the Nobel Prize was awarded a little bit early, in that Feringa and Sauvage came up with the idea that these molecules exist without them necessarily having a very clear practical application or use. So the example I showed of the molecule behaving like a car, the primary, most promising application is for transport. So you might be able to pick something up at the molecular scale and move it in sort of a conveyor belt fashion if you line up a number of these molecules. So perhaps when you're on the left-hand side, you pick something up, and as you move around to the right, you drop it off and you pass it on to the next one. But it's more of a kind of a blue sky research opportunity where once you build the technology, then hopefully the applications will come.
Thank you.
I was just going to concur with Anne on congratulating and commending you on the use of visuals to help us to understand, but also the use of analogies as well there, Fletcher. And that was a great question from Anne, because I was thinking that you've certainly made it very clear the significance of your research and your team's research and how you've developed on those ideas, but really solved a challenging problem. And then the next step would be the real world application, and I was interested to hear that too. So thank you.
Yeah, just jumping off something that you said, I was genuinely quite surprised that in a semester-long research project, by taking what was thought of as a really complex problem and kind of simplifying it and taking it right back to its first principles, that me coming out of undergraduate chemistry and physics, that was kind of, I was familiar with those kind of problems. That if you look at a problem like this at that level, then you can actually make some meaningful ground. And so now if you were to go and do a more complicated simulation, this simplistic simulation can kind of guide you and go, okay, we need something that's asymmetric. We need something that has this kind of ratio of on to off. And you can narrow in and hopefully make some more progress with the more complicated stuff.
Wonderful. Look forward to seeing what happens in this space.
Thank you, judges. We have a question from the audience too for you, Fletcher. So can you explain more about complex real system and the definition of random force in random force from solvent?
Sure. So I'll start with the second part of that question. So it's random in the sense that it acts equally in all directions. So I don't know how much background you have in physics, but we think of heat as something that's random. It acts in all directions and it's dispersed, whereas work, that's something that's directed. And so the heart of the problem is that we need to get these water molecules that move in all directions and don't seem to have any sort of order about them, and take advantage of that to try and get some sort of ordered motion. And so the random force from the solvent is the collisions that come from interactions with these water molecules in all directions. And the complex real system, so when you're trying to simulate a real system, rather than simplifying these interactions as a single equation and a random number generator for how often these collisions occur and how strong they are, you instead need to build a box, essentially, and populate that box with maybe one catenane and 1,000 water molecules. And every time step of your simulation, you need to see where each water molecule is and calculate the force of its interactions with every other water molecule around it. And so you're doing that for thousands and thousands and thousands of interactions. And so it very quickly becomes very computationally expensive, and depending on what sort of level of interactions you want to get to. So I talk about collisions, but there are also things like hydrostatics. So molecules have charge, and charged things can interact. And so there's a whole multitude of layers of complexity that come in from actually looking at real systems that we can conveniently ignore by looking at a simplified problem.
We have another audience member who wants to ask a question. I'll just allow them to. Yep, you can unmute yourself.
Hi, Fletcher. When you're attaching and detaching your molecules with the blinking, how do you get the attached group to attach back on again in the same direction so that it doesn't undo your whole unidirectionality thing?
Wonderful question. So it's an assumption of the model that it always attaches the same way around. It's kind of a problem for the experimentalists to make sure that it always does what I want it to. But you're right. So I assume that it always attaches such that the bulky parts in the same direction. Good luck, experimentalists, actually getting a system that does it.
Thank you.
Great. There were some very good questions. Thanks, Fletcher, for that great presentation. Let's move on to our next presenter. That's Tiarne.
Thank you, everyone.
I'll just share my screen. Click share. Can you see my screen? Yep. Okay, and I'm all good. All right. Hello, everyone. Good afternoon. My name is Tiarne, and today I'm presenting to you our work on a click chemistry approach towards a new triazole-based class of self-immolative polymer. But before I begin, I'd like to acknowledge my co-authors on this research, Anne-Marie Kenny, Yuan Long, and my supervisor, Dr. Derek Roberts. So it goes without saying that synthetic polymers are ubiquitous in our everyday lives. They provide innumerable benefits to society, not only for preventing food wastage, but also to public health and medicine, to transportation, in construction. Plastics are everywhere, so the list really does go on. And the uses for polymers or plastics are largely derived from the very broad range of properties that they're capable of exhibiting, not only in their flexibility, their strength, their chemical functionality, and perhaps most importantly, their ability to resist breakdown under certain conditions. So naturally, this presents a rather large double-edged sword for us, because the properties that make them useful are also the properties that can contribute to their pernicious wastefulness. And the reason for this lies in their pathways to degradation. So in this simplistic representation, consider any polymer as something akin to a string of beads, where each bead is a single monomer, or the smallest repeat unit as a part of our polymer. And the string connecting each bead is the chemical bond that forms between these units. For the complete degradation of any conventional polymer, for that to occur, the string needs to be cut at each and every one of the points between these units. So depending on the class of polymer, this can occur either mechanically, where you physically force them apart. It can occur chemically, where you apply things such as heat or pressure or other chemicals. Or in the case of biodegradable polymers, you can use naturally occurring enzymes or organisms to do the job for you. But irrelevant of the cleavage stimulus, this generally results in many small polymer fragments, leading to the creation of what we know as microplastics, rather than complete degradation, which can take significant lengths of time to occur, as we're all aware. However, more recently, a new class of polymer with an alternative degradation route has come to prominence, and they are known as self-immolative polymers, or SIPs for short. Now, SIPs are a special class of polymer that are kept stable only by their end group, or their cap, which is represented in the simple model on the screen by the red pentagon. Now, upon cleavage, or effectively the removal of this cap, a reactive end group on the polymer is exposed, initiating a cascade of depolymerizing reactions that is akin to the lighting and burning of a fuse, hence the name self-immolative. Now, in some classes of SIPs, the molecules that are spit out at the end is the monomer itself. But in the majority of classes, the product of these reactions are actually smaller molecules that make up the already small monomers. And so therein lies the two key differences between the degradation pathways of SIPs compared to conventional degradable polymers. Firstly, their continuous degradation occurs in response to a single, very specific stimulus or triggering event, as opposed to requiring continuous exposure to the stimuli in the case of conventional polymers. And secondly, because the removal of one end group results in the release of many small molecules, the outcome is actually an amplification of the stimulus event. So naturally, the unique properties of SIPs make them applicable to many new applications, and they're now making their way into emerging technologies for sensing, for imaging, as well as the controlled release of latent molecules in the case of drugs. However, despite the seemingly boundless potential that this implies, they're not without their limitations. So unlike the multitude of conventional polymers that we see every day in use, there's only a relatively small number of classes of self-immolative polymers that have ever been known to be successfully synthesized, which harkens back to Fletcher's comment about good luck for the experimentalist. Now, this is largely due to the fact that there is a limited number of known mechanisms by which self-immolation can occur. So the current motifs degrade by either one or a combination of the following two mechanisms. The first is cyclization, where the reactive end of our polymer attacks another part on the polymer, forcing and ejecting out a small cyclic molecule. The other mechanism is an elimination mechanism, which also ejects out a small cyclic molecule. However, this time it's in response not to an attack on the polymer, but in response to the flow of electrons from the newly exposed end back into the polymer itself. And to this extent, the overall aim of this proof of concept project was to synthesize a new self-immolating motif that contained an alternative type of elimination mechanism, where in our design, this electron flow occurs across a triazole ring. Now further, another interesting point of our design is that this triazole ring is not part of the monomer, but rather it's incorporated into the polymer backbone during the linkage of the monomers themselves via a very well-studied azide-alkyne click cyclization reaction in the presence of a copper catalyst. Now, the processes involved in achieving this can be broken down roughly into three broad steps. The first step, or rather a series of steps, was to synthesize the monomer with both azide and alkyne terminal functionality, such that it is capable of undergoing the polymerization reaction of the aforementioned click reaction. Now, what we can see on this slide is the chemical structure of the monomer, Notice the lack of rings in it. The triazole is not contained in the monomer. And for ease of conceptualization, I'll simplify it to this. Now, this does look a little bit different and a little more colorful than the bead representation from earlier. And that's because our monomer is not itself commercially available. The first step was that we had to make it. And this was done through a series of reactions where we've taken smaller starting materials, small molecules that are commercially available, and we're sequentially adding them to the product of the preceding reaction. In other words, this isn't all happening in one pot. We needed to purify the product of each step and characterize it using specific techniques such as NMR or IR spectroscopy, so that we can confidently say, yes, we know what it is we're adding to the pot each time. And the end result of each step is that we've added some new point of functionality to our eventual monomer. So once we'd made our monomer and confirmed, yes, it is what we think it is, our next aim was to make the polymer. Keep in mind from the chemical structure of the polymer that you can now see the ring is present, although again, I'm going to simplify it to this. Now, in contrast to the complex synthesis of the monomer, polymerization is a one-pot reaction where effectively all we had to do was mix all of our monomers and our copper catalyst all together in a single tube and leave them to polymerize by the click mechanism that I described earlier. And further, because this is a proof of concept project for this self-immolation design, we actually mixed in a cap in a 1:5 ratio with the monomer. Now, this cap doesn't have the dual terminal functionality that our monomer has. It only contains the alkyne end. So effectively what this means is that we're only going to form short polymers, or oligomers as we call them, which had a mean length of only 5 repeat units of the monomer. And we did this because the shorter oligomers makes it a lot easier to study the reaction kinetics of polymerization, so how quickly the monomers actually click together. But it also makes it easy to study the degradation reaction, which leads us to our third step. So once we confirmed that we had successfully made our polymer via techniques as NMR, but also mass spectrometry and size exclusion chromatography, the final step was to degrade the polymer in response to our designated stimulus, which in this case, we designed a cap that could be cleaved by a palladium catalyst. And we then monitored for the release of the self-immolation products, which you can see here. But I'll simplify to this. And notice that the color and shapes of these products are not the same as the starting materials that we used to build the polymer, or the monomer, sorry. And this is an indication that the degradation reaction is not reversible because we're not putting out the same thing that we've put in. Now, as with the polymer synthesis, this too was a one-pot reaction in which the polymer and the catalyst system were all mixed together in a single tube, during which time we monitored the kinetics of the reaction via time course NMR experiments. And the results of these time course experiments can be summarized here. What we see in this graph is the appearance over time of certain chemical environments that we would expect to see on our predicted self-immolation products. So they're the purple and the green lines that are seen to be increasing from the bottom. Now, these are changing in line with the disappearance of certain chemical environments which were unique to our polymer. So not only does this tell us that our polymer is degrading the way that we're expecting it to, but we can also glean additional information about how fast this is occurring, which you can hopefully see on the graph is occurring across the order of a couple of hours. You might also note that the lines asymptote to around 50% completion. So only half of our polymer is degrading. And this is something that we would be interested in looking at improving on in the future iterations of this design, alongside exploring experiments for creating longer chains of the design, because 5 repeat units is not particularly long or particularly useful, as well as exploring ways to incorporate different caps that can respond to alternative triggers and incorporating other functional elements into the backbone of our polymer. So thank you very much for listening. Here's my acknowledgement slides, as I mentioned earlier on at the presentation. Now, are there any questions?
Thanks for that presentation. So judges, do you have any questions? And again, audience, if you have any questions, please put it in chat or raise your hand. Judges, you can go ahead.
Very nice use of graphics to illustrate a very complicated subject for us laypersons. My question is essentially, it comes back to something a bit similar to my question of Fletcher. While I understand that you're presenting some chemistry, when you have a non-technical audience, tying it back to the exposure that the audience has will really help getting people's attention. And there's 2 points where I thought that could have been built into your presentation, and to some extent this applies to you too, Fletcher, is not just at the end where perhaps the question of what does this mean for us? Does this mean less plastic bags hanging around?
Yes.
Can I just say, I did do chemistry once a long time ago, and I can kind of put a few pieces in place myself, but I suspect that there are people in the audience who couldn't. And similarly, you could have finished with that kind of real world, and now I'm talking about your presentation technique. It would have been great to have something like that as an example of a real world problem right back at the beginning. So, photos of plastic bags hanging around, floating around outside the tip, or, something like that would have made it a bit more real for the audience.
Yeah. No, thank you very much. That's important. Yeah, thank you. I'll incorporate that note, I think, next time if I present.
But the other thing is, you could clarify for me, is it actually going to save us plastic bags, or I'm just guessing there, but where does this go?
Yes, and that's a question I think I was definitely anticipating, because similar to Fletcher's work, it's still blue sky research, and I guess with any polymer, not just self-immolative polymers, but any conventional polymer even, until you can even make it, you can't study you don't know what properties it's going to have until you've even made the polymer itself. And then you can, I guess, material scientists will study the properties, and it's only once you know the properties that you can start to see where this might be useful. So like I said, some of the current applications are in sensing and amplification, so they're not even necessarily in plastic or something that we know as plastics. They're kind of still kept as small things that amplify molecules, but it could be that this design, if we're able to make longer chains, like I said, we only did 5 as the proof of concept to see if this even works, but if we are able to make longer chains, it could be that this could be the perfect material for plastic bags that, like you said, degrade. Although there is a key point, I guess, in the trigger that cleaves off the cap and makes the reaction occur in the first place, is thinking about designing triggers that could degrade in the environment, but not degrade when you still want to be using the bag. And so that might be tying into more a societal problem of how do we think about recycling? Could we be returning clothes back to the manufacturer once we're done, and they have, say, the palladium catalyst? Like, it's not often you're going to be drenched in a palladium catalyst wearing a t-shirt made of this polymer. So it comes down to if we can make a longer version, what are its properties? And then once you know its properties, then you can start to get an idea of what applications it can be used in. But yes, very good point.
Thank you, Tiarne.
Thank you, Tiarne, for a lovely presentation. And just concur again with Anne in a sense that it is a general audience, and there were very technical aspects of your research, and it would be wonderful to have that sort of problem in the real world for your general audience. But as I was listening, you said that there was application in terms of sensing, imaging, and drugs. And I was wondering if you could elaborate on that and just connect your research to those applications.
Yeah, definitely. So the actual self-immolation design started from drug research, where the idea is you have a part of your drug that is the identification part of it, that actually localizes the drug to the part of the body, and that could be an antibody or some other kind of localization mechanism. You need to then link your drug to that localization part, and self-immolation linker molecules were one of the solutions to that, because it could often be, if you have the cleavage event in response to, say, a more oxidative environment or a lower pH or some stimulus that's specific to the part of the body, then the linker will essentially disintegrate away, and you're left with your drug perfectly delivered to the part of the body that you wanted it to go to. So that's where it initially came from. And then I think that started about the 80s. And it wasn't until 2008 that someone was like, well, why do we need to stop at a linker? Why can't we make something that's continuous, like into a polymer that can then self-immolate? And so that's what the sensing and applications are, because if you only have one linker, you have one cleavage event and you might spit out 5 small molecules. That's not really, in terms of sensing technologies, that's not really enough of a signal to receive anything. But if you have a polymer where one signaling event spits out many, many, many small molecules, that amplification event, then suddenly you might have a signal that typical kind of, just thinking of conventional machines that we use to sense molecules in any solution, that they can actually, you're at concentrations that they can start to sense. So polymers are kind of a different approach then to just that single linker, which is what they started as. And then there are heaps of different other designs that self-immolation is also taking. So polymers is just one approach to that. Yes.
Thanks very much.
Thank you.
Thanks for that. So we have 2 more questions for you from the audience. So the first is it possible to reclaim the residual bits to make more polymers? That is, are these polymers recyclable?
Good question. So there are certain types of self-immolative polymers that do collapse down only into their monomers. And if you do spit out the monomer instead, then it is possible to reclaim the monomer and then remake the polymer. Not in our design, because like I said, the small molecules that are being ejected out after degradation are different to the ones that we've used to make the monomer in the first place. And I think even if they were the same small molecules, the conditions required to make the monomer are so controlled that even if you spat out the same things, you wouldn't be remaking the polymer. But there definitely are types of self-immolative polymers that do that, and their trigger is often heat. So it's like a sealing temperature, and once they hit that temperature, it's enough to break one bond, and then it collapses into the monomer. And then once the sealing temperature goes back down again, the monomers can reform back into the polymer. So it comes down to the design. Not in this design, but definitely in some designs you can do that.
Great. There's another question. So what are the commercially available starting materials used in the stimulation?
Oh, I do not know the chemical names of them on the top of my head. I can find, if you're interested in seeing the actual chemical structure of what that looks like, I think that has the names on it. But they're really just, hold on. These are the names of it. Yeah, I might have to go back to my paper and find the actual names of them, but they're really just small molecules. You can see here, this is, yeah, they're just very small. It's an alcohol here, a benzene ring there. Like you're just slowly connecting little pieces on each time. It's probably unnecessarily complicated, but yes, I'm happy to share the things if you would like. I'll go and find my paper. Yes, any other questions?
I guess that's all we have. Thanks for that great presentation. Now let's move on to our last presenter, Ziqi. Whenever you're ready.
Let me share the screen. Okay, is the screen share working? Yes.
Yep.
Okay. Cool. So I'm Ziqi. I'm a second-year undergrad at the ANU, and today I'll be talking about the helium content in low-mass stars and using that to find a diagnostic for the chemical evolution of our galaxy, so rather the other end of the size scale. In the beginning, there was the Big Bang. And during that, a period of element formation created by mass about 75% hydrogen, 25% helium, and basically nothing else. And so gradually, with processes like stars fusing hydrogen into helium, then heavier elements, which we refer to as metals, and things like stars going supernova, the universe is gradually enriched with elements heavier than hydrogen. And we can look at these mass abundances, and we denote them by Y for helium and Z for metals. And when we look at the past of the universe and of our galaxy, one of the things that we're really interested in is, how does this enrichment process proceed, right? How fast are elements being formed? And one of the diagnostics we can use for this is the helium to metal enrichment ratio, which is essentially a ratio of how fast helium is being produced relative to metals. And so to measure this, we'd like to look at the composition of the universe or our galaxy sometime far in the past. And we can look at this through stars, which are generally rather long-lived, and we can make measurements of their chemical compositions. The problem is, though, while we can measure metal content for stars relatively easily, we can't do it for helium. We can directly measure helium content only for very massive stars, but those same stars also are very short-lived and burn the hydrogen fuel into helium at a blistering pace. So whatever value we measure is very different from when the star was first formed, and it ends up being not conducive to this kind of study. And so past studies in this subject only had access to samples of a large handful, and with recent stellar surveys returning measurements for much larger stellar samples than before, the aim of this project was to determine the helium content for a large sample of stars and apply that to find this enrichment ratio. And so this comes in two parts. First is finding the appropriate stars for the study, and the second is to find the helium content. And we want stars that don't have a sort of fast evolution. And to visualize that, we can look at the temperature and brightness of stars. So if you have a large sample and plot the stars along these two axes, you get what is called the hertz-sprungrussell diagram, so shown here. And as stars burn their hydrogen, they become hotter and brighter and evolve upwards through this diagonal section called the main sequence. Now, large stars, massive stars do this very quickly, but low mass stars don't. So when we look at the low mass region of this diagram, stars here have lifetimes longer than like the current age of the universe. So in the stars, there hasn't been much hydrogen burning going on, and it ends up that their chemical compositions are representative of the gas from which they were formed and of a much older universe. And so zooming in, I take my sample from the Australian Galar survey of about 25,000 stars, so rather a bit larger than before. And we can begin by looking at the metallicities, which we can measure, and we see that there's a relationship. As stars become richer in metals, they also become cooler, and as stars become poorer in metals, they become hotter. And in fact, because these low mass stars have so little evolution going on, their position on the HR diagram is defined up to dependence on mass only on the chemical composition. And so we can compute models for this and plot them on the HR diagram as shown in the figure here. And so the dotted lines represent stars of the same chemical composition, and as we increase helium, stars become shift essentially directly horizontally, become hotter. And so for the sample of stars, we have accurate measurements of metal content, temperature, and brightness, and we can also predict the position based on chemical composition. So by fitting the stars parameters to theoretical models, we can therefore infer a value for helium. And so we can't do this analytically, unfortunately, but I can do it numerically by fitting one variable at a time. So you end up with a function in sort of 3 parameters, and it's a bit hard to visualize, but we begin with computing models for a grid of initial chemical composition of the stars, and this is propagated outwards from solar parameters. And so from here, we first fit for each star the brightness of the star to each of the stellar models to find corresponding temperatures. And having fit one variable, we're left with helium as a function of temperature and metallicity, metal content. And now we're down to 3 variables, which is a little easier to measure. So recalling that for our grids, we're computing models for a set of constant metallicities. If I plot the points in the helium versus temperature plane and join stars with constant metallicity, there's actually a linear relationship. And therefore, we can interpolate along the metallicity axis, so the dotted lines here, and find the appropriate relationship for a star with the same metallicity as each of the stars in the sample. And by extrapolating from this, we can find the appropriate helium. And so applying this to the entire sample, we find this plot, which is helium versus metallicity for the entire sample. And it's generally well behaved, except for one little region around here, which is around the solar metallicity of 0.017. And that is due to limitation in this process. Because we're building the models outwards from solar, the interpolation breaks down when the stars have metallicity near solar, and we lose the linear relationship. But other than that, we do find a very generally well-behaved linear relationship, and that allows us to take the gradient and hence find the Dirichlet ratio for our galaxy of about 2.1. And so what this means is that on average, processes in our galaxy produce helium at twice the rate of metals. And so that's the general study. And following on, I'm currently extending this with a denser grid of models and the different interpolation method to circumvent this limitations around solar metallicity. And I think more excitingly is the main point of this is that I was able to find helium values for a much, much larger sample of stars than before. And this large sample size allows us to further, in the future, look at this evolutionary behavior in different stellar populations within our galaxy, and hence to look more precisely and in much further greater detail at the chemical history of our galaxy. So I think that's the really exciting part, and there's a lot to go from here. Great, thank you to my research supervisor, Dr. Catherine, and yeah, that will conclude the presentation.
Great presentation, Ziqi. Judges, do you have any questions?
So, Anne, did you want to start?
Look, I'll just make the comment that I loved your opening. Sorry, not the opening slide, the one with the introduction, but the title, but the actual introductory slide. I love the use of the stellar background, presumably somewhere in the Horsehead Nebula with lots of stars being generated. It would have been nice to finish that previous slide to this one with a similar background. It would have tied back your final message to the idea of stellar evolution and to the chemical composition, and the use of something, not the same graphic, something perhaps in different colors, possibly even a different dust cloud. But yes, that would have given your presentation just that wee bit of punch in that final moment, because you're up against the problem that for a lot of people, stars are a long way away.
Yes.
So, you know, making it sort of meaningful for the audience in this particular case, I think, you know, was a tougher ask on you, but I think you could have used graphics a little bit more to help you. But no, very, very clear presentation, and thank you.
Thank you.
Thank you so much, Ziqi. Yeah, and I really liked it was nice that you had a slide also to indicate basically what the problem is, and you were saying how it was very difficult to measure helium content. And I guess you were talking earlier about the understanding chemical evolution, and you came back to that towards the end. Yeah. And it was good to see, because you allude to the insights, and I just was thinking, what are the key insights that you've gained actually from this about the specifics of the chemical evolution, would you say?
So for this specific project, I suppose the context is in the past studies working with something like 80 stars or so. So before sort of, how should I say it? And so because of the small stellar sample, the results of the studies generally have very large uncertainties. So you'd end up with something like a value of 2.3 plus or minus 1.6, right? Or otherwise different inconclusive results. And so the sort of recent stellar surveys producing this large amounts of data generally are relatively recent, I think. So my sample is taken from the Australian Galar survey, which began, I think, in 2014. And that has, in overall, measured parameters for something like 600,000–700,000 stars. And the older papers, I think, if I recall correctly, were working with the Hipparcos catalog, which had about 100,000 stars, but with small uncertainties in only like 20,000 stars, and that's already smaller than this sample. So far, this part is mostly about extending previous methods for a recent, much larger available sample, and then from here we can begin to look at stars in different regions of the galaxy. So the galaxy is comprised roughly of sort of like the disk, right? Which is what we see in all the pictures. And then, but you also have like the bulge and the halo around that. And you can look at more specifically, which we haven't been able to do just because of the sample size.
So we can study stars
like in specific regions of the galaxy.
Yeah, and it sounds like that with the access to more data, you're able to get to measure more accurately the helium content. So 2.1, was that right? And then, so I guess what I was seeking was more of a take-home message for our general audience about the chemical evolution. So what can you say about that?
I think it's kind of hard to put it in like a meaningful way in terms of application to real life, right? But
yeah, I agree.
I guess physically it's like, stars and everything produce twice as much helium as everything that's heavier. But yeah, so you can't really have like connected to real life in that sense, other than like stars are really cool. This is what's happening.
No worries.
Yeah, but
thank you.
Thank you for that. Ziqi, we have a question from the audience. So can you give us a bit more insight into how did the parameter fitting in terms of the process and challenges along the way?
Right, so processes and challenges. So I suppose a lot of the methodology is dependent on how you get, where you calculate the models at. So for this specific project, I had access to models calculated in sort of this region. And so because the idea is you're fitting the other stellar parameters and finding the appropriate helium value. And with something like this, it's rather incomplete, and you miss out on rather large swathes of initial chemical compositions. And so you have to try and, in the end, do some sort of extrapolation to fit most of this region. And that leads to this sort of fitting one parameter at a time until you can get some sort of linear relationship or other that you can actually properly extrapolate into the rest of the plane. And that leads to this final challenge of everything starts to break down when you approach the point that you build out from. And so the actual process is not too complicated. You just do a bunch of interpolations and find points corresponding to each value. But it's more how do I avoid this in the future. And so right now I'm sort of doing an extension on this, and I'm working with really dense grids, like an actual grids in terms of this chemical composition. And so with that, I'm trying something with like Bayesian sort of minimization. So similar to chi-squared minimization techniques, if you're familiar with that. And then that is more robust than trying to interpolate and then extrapolate, and then you end up with a bunch of errors in a specific region of the plane. Yeah.
Great, thanks a lot. So that brings us to the end of the session. I'd like to thank the judges again, Anne and Dwi, for being here. And congratulations to the student presenters for some great presentations, and especially for the audience, very interactive, great questions. And yeah, thank you all. The recording will be available online after the conference, and hope to see you in other events. See you. Thank you.
Well done to all our presenters. Thank you.
Indeed.